these things.
Yes.
Then the competitive Industry 4.0 carries a meaning in the minds of the youngsters. If they
Yes, sir.
know these things, definitely they can build up and bring in more and more technology to be used in the industry. That way, a true combination of industry and academia will take place. I feel more such webinars to be done, and again, Dr. Vishwas, for having spared your valuable in educating our faculty and students with the latest technology that is applied in the industry. And I should congratulate Dr. Kapilan and his entire team for successfully launching this and conducting such very useful and eventful exercise like Industry 4.0 webinar. I congratulate Dr. Kapilan and his entire team. I wish the event to be a successful one. It's a 1 week program, and output of this 4.0 should come out as a compendium so that that can be shared in the copy forum among all the participants for further reference. Thank you very much for giving me the opportunity. Please convey my regards to Sri Ramas and his entire and his family also.
Sure, sir. I'll do that, sir. Thank you so much.
Thank you, sir, for your informative speech and encouraging us to organize this type of program. Now I request Dr. Vikanamurthy K, Principal NCET, to address the gathering.
Everybody, am I audible?
Yes, sir.
Yes, sir.
Yeah. Esteemed guest and resource person of the today's webinar, Dr. Vishwas, and respected director, Dr. Gopalakrishna, and other dignitaries, students and faculty members. At the outset, I would like to say that we are very happy that Dr. Kapilan and team, they are very active in this lockdown period and conducting various workshops and webinars which are very much useful to the students as well as faculty members. As our director and Vish was telling, now today we are entering to all smartness, smart people, smart city, smart machines and so on, and the whole paradigm has been shifted to the latest technologies like artificial intelligence, machine learning imparted into various disciplines in not only computer science or electronics, including mechanical and even civil engineering as well. And data science is getting very, very important aspect nowadays, and it is a high time for the faculty and students, because faculty also update with their knowledge, and students has to develop the skills. Today only skill oriented jobs are more required, and all industry or whatever that is they are expecting skills. So it is the right time for everyone to update their skills. In this regard, the webinar on Industry 4.0 is very much right and useful, and congratulations to Kapilan once again for having arranging this for the benefit of the fraternity, teaching fraternity as well as students. And I hope the students and faculty members will get maximum benefit of this 1 week webinar, and I hope the program will be successful. I wish everyone all the best, and I thank for giving me an opportunity to speak in this occasion. Thank you, everyone.
Thank you, sir. Now I request Mr. Balaji to propose vote of thanks.
Good morning, one and all. Sir, am I audible, sir?
Yes, yes, continue.
Yeah.
Good morning, one and all. Honorable Chief Guest of the day, Dr. Vishwas R Puttige. Respected Guest of Honor, Dr. S.G. Gopalakrishna, sir. Respected Principal, Dr. Srikanth Murthy, sir. Respected HOD, Dr. N. Kapilan, and dear participants. I consider it a privilege to propose a vote of thanks to all the dignitaries on behalf of Mechanical Engineering Department, Nagarjuna College of Engineering and Technology. I take this opportunity to express my deep gratitude to Honorable Chief Guest Dr. Vishwas R Puttige for accepting our invitation to be chief guest and resource person for today's program by taking out valuable time for his busy schedule. Thank you, sir, for your insightful address. Thank you very much.
Thank you. Thank you.
I express my sincere thanks to our director, Dr. S.G. Gopalakrishna, for his constant support and motivation in all our activities. And I thank for your thought-provoking address, sir. Thank you very much, sir.
Thank you, Balaji.
I extend my sincere thanks to our principal, Dr. Shrikant Murthy K, for providing encouragement and support in organizing this program. Thank you very much, sir.
Thank you, Balaji.
I thank HOD for organizing this webinar in this need of hour, where he has taken a lot of efforts in making this program executable. Thank you very much, sir.
Thank you, Balaji.
I thank all the student and staff coordinators for their support and cooperation in making this program a successful one. Finally, but not least, I thank all the participants for turning up in large numbers to enrich their knowledge in latest technologies. Thank you, one and all. Over to you, sir.
Kapilan.
Yes, sir.
Kapilan.
Yes, sir. Yes, sir.
How many viewers are there on the YouTube now?
Check it, sir. Actually, totally around 400 participants have registered. We have given 2 YouTube links.
This is across the country or across South India? How is it?
Across the country, sir. Actually, we have participants from other states also.
Other states also. Okay, very
Yes,
good.
sir. Maharashtra, Tamil Nadu, Kerala, Karnataka.
Very good. Okay. Finally, you make a compendium. You just in the form of at least a soft copy also. The output of this webinar should be consolidated and then you send it across to all the participants. It will help them as a guide.
Okay, sir.
Okay, right. Go ahead.
Sir. Thank you, sir.
Over to, I think, Vishwas.
Yes, sir.
Yeah, you can start your presentation, sir.
Okay, great. Thank you. So thank you again. I'd like to start with by thanking the organizing committee here for giving me this opportunity. As you all know, a lot of people have known about additive manufacturing, but I'd still like to run through the whole process and also state some of the applications, advantages of additive manufacturing, and then wind up with some good case studies and examples of how it's being used today in the industry. Next. So, so basically, additive manufacturing is only a terminology which is gaining a lot of prominence now. It has been in existence for the past 40 odd years, when it has been known by different names in the past. And only now it's gaining a lot of importance and momentum because industry is accepting it well and using it for various applications. So just a quick intro about AMACE Solutions. So we are basically a service bureau, which means we provide end-to-end 3D printing solutions. We are a part of Ace Micromatic Group. We are basically a joint venture between Ace Designers, which is the largest CNC turning manufacturing company, and Ace Manufacturing Systems, which is the machining center company. Sir did mention about that. And basically, we are the additive manufacturing wing of Ace Micromatic Group. We are fairly young, but we've been offering services to different industries today. You'll have a look at some of the examples. Next. So basically, we have seen different types of traditional manufacturing. Just a quick intro on that. We know mostly parts that we use, we feel we see around us are all either casted through a casting process or formed using a press, as you can see there, joined using a welding process, as you've seen, and finally taken up for machining. So this is normally how traditionally any metallic object is done, broadly classified into. But going ahead, in the machining, we have aspects such as turning, milling, drilling, tapping. These are all different processes in subtractive manufacturing. So in the conventional manufacturing process, we call this as subtractive manufacturing. I'm sure a lot of us from the mechanical engineering stream would have studied this, used these machines, and actually felt the process. So bulk of the manufacturing today, be it any automotive part, which is especially important in our transmission and movement, are all subjected to these subtractive manufacturing processes where you have material being removed. So why is it called subtractive? Because material is removed from an existing state. It could be from a casted part or a forged part or even a solid block that is machined. So finally you remove material to get your final part. So that's why it's called a subtractive manufacturing. On the contrary, additive manufacturing is basically a process where you put material together. So what you see here is a small comparison where in a subtractive, you start from a solid block and remove a whole lot of material, and then you finally get your final part. Whereas in additive, you start from a material which is fused either through a heat source or laser or electron beam or a binder. We'll see some of those processes where you basically put the material together just enough to get your final part with very minimum wastage. So that way, this is a very green process. So it's a very natural way of doing things. So next. So this is an interesting curve which again substantiates the comparison between additive and subtractive. Focus on the x and y axis here. On the x axis we have complexity, and on the y axis we have cost. So the green line here, what we have is basically how we would go about costing a part which has to be made conventionally. So conventionally, any part, when the complexity goes up, your cost shoots up drastically. So as if your part needs a fourth axis to be used to machine a part, or a 4-axis machine, or a 5-axis machine, then the cost shoots up dramatically. So because of this, what happens, most of the designers end up simplifying their design of their parts so that complexity reduces. They break the large complex part that is required finally into smaller pieces which could probably be machined or manufactured using simpler processes. So this is how conventionally parts are being done. Whereas with 3D printing, your complexity is pretty much free, which means irrespective of how complex a part is, the cost remains the same. The only aspect that actually that decides the cost is the material, the amount of material that goes in, and also the volume of the part. I mean, how is the volume of the part being printed? So irrespective of that, the cost remains the same. So which means you could have a very complex part weighing X grams that is being printed, or a simple solid block of X grams being printed, the cost would remain the same. So that way, you're better off choosing the part which is more complex when you decide to use the additive manufacturing process. So what we have is that small red line that you can see there, which is dropping straight down to the x-axis, which is basically the tipping off point, which says any part which is complex beyond a specific point, then it doesn't make sense to use the conventional route. You're better off 3D printing it. So that's basically what is being shown here. So anything beyond that red line, which is called the break-even point, irrespective of the complexity, the cost will remain the same. But something simpler, very straightforward, that can be done the conventional way, it doesn't make sense from an economical point of view to go for 3D printing or additive manufacturing. So this is basically the whole gist of this slide here. So what you see next is basically advantages of additive manufacturing. So what we have seen, most of the current manufacturing route is all subtractive in nature. So you've seen whatever we've mentioned earlier, most of the automotive, aerospace, medical, you take any aspect of manufacturing, they use subtractive routes. But the natural way of doing any object or creating any object is the additive way, be it a tree or bird, an animal, the human body, all of them are being made actually the additive way. We don't get an arm or a leg which is screwed into us or joined as a separate member and then put together. We are actually formed the additive way, where we are formed as a monolith structure and then we grow internally. Another advantage is simplified product design. So what 3D printing does is it allows you to make product design very simple. So what when you conventionally design any part for a specific application, you always have a constraint from a manufacturing side, either from a casting guy or a forging person who's going to be telling, look, this cannot be done. Or you'd have constraints from a machining person who'd end up telling, look, I cannot insert a tool to do a hole or mill it at a specific angle, so you'll have to break it into multiple pieces. Or even assembly, for all you know, because you cannot assemble it together in its current complex state. So whereas with 3D printing, you can print assemblies, which means you're not worried about how the input processes. You can directly print assemblies. We'll be looking at some of those examples going ahead. So that's a big advantage. Interestingly, if you've seen metal tools, we discussed about conventional components which are being 3D printed, like the ones on the top left. But what is also happening in the medical field, one of the most prominent areas is dental copings. If you actually see, one of the latest technologies being used by dentists is to print dental copings, which is what a cap that you'd want to be inserted onto your tooth, which is probably spoiled, is for done through maybe a 3D scanning of your tooth, and then that is converted into a 3D model, and then a dental coping is printed. So here, irrespective of the volume, what the 3D printing manufacturer does is he would get input from different dentists, and they're all printed together on a single block or a single plate. So you're basically doing something called as mass customization. When we say mass customization, you're producing something in high volumes, but they're all customized parts. They're not necessarily high volumes of identical parts. We all know mass production. Now mass customization has become, mass production has become mass customization, wherein you're printing, 3D printing for every specific patient individually, but in high volume. So volumes will remain, but they're all going to be customized. Similarly, you have prosthetics, you have orthopedic implants, various medical implants that are happening. Then, of course, what used to happen conventionally in 3D printing was rapid prototyping, where you'd want to get something done in a small plastic to mainly for visualization purpose. That is happening, that you've seen, known, most of us know about that. Interestingly, a lot of homes are being printed today. You have concrete printing machines which can print bridges and homes in very difficult environment. And in fact, even for speed, today we've known of 3D printed buildings which are done in less than a month's time, multi-floored buildings which are printed in less than a month's time, which is all because of 3D printing. Food printers, we have, interestingly today, food printers which can print cakes and pastries and biscuits and cookies and chocolates, all in different shapes of either characters or different persons, humans also. There are apparently food printers sitting in a space station where astronauts who go up there need hot, fresh food. They can press a button and food gets printed there. So like this, interesting applications. Jewelry is another interesting field because you can print them really light. Lightweighting is one of the key applications of 3D printing. So a lot of interesting people have started printing gold and other exotic material where make it look big and bulky, but it's actually hollow or lightweight from inside. And they can also be with a very intricate design. So this way, different applications. Now, going ahead, one of the biggest subjects in additive manufacturing is DFAM. We call it as, it's actually design for additive manufacturing. We've all learned about design for manufacturing, but this is design for additive manufacturing, wherein the subject deals with a lot of optimization, be it weight optimization, topology optimization. It basically means taking a part which needs to be, which you'd want to be printing it, where we do a lot of design change, modify it to make sure you reduce the weight, reduce the unwanted redundant aspects of the part, and make it just enough and make it suitable for 3D printing. We'll have a look at some of the examples going ahead, but other advantages is part consolidation. I explained that today people are 3D printing consolidated parts, which means you could have multiple pieces of individual parts which are all put together as a single assembly and then printed together. Now, this also helps you in direct part replacement, which means where you'd have spare parts and aspects like that, you can reproduce them very quickly and then replace them, which is a big application today. And of course, we've always known rapid prototyping, where high volumes of where you'd have a lot of prototyping to be done before any development of maybe an automobile or an aircraft. All of that can be prototyped using 3D printing, which is a key advantage today. Going ahead, normally we classify additive manufacturing or suitability for additive manufacturing based on quantity. Now, take an example. Now, say, for example, you have a part which is very low volume, say less than 250. 250 is just a figure there, but you could have it as any number based on application. So if it's a low volume and if the geometry is machinable, then normally people go for a CNC route. But if the geometry is not machinable, then we suggest just printing those parts because your volumes are too low to be even die casting it or injection molding it based on what part you're making. Now, whereas if your parts are high in numbers, where you want high volumes of parts to be manufactured, and if your geometry is machinable, then you'd go for an investment casting or a die casting traditional route that you'd follow. But if your geometry is not machinable, then we'd suggest printing those patterns through your investment casting patterns can be printed using 3D printing route, where you could print aluminum or any other material and use them as patterns, so you don't have to actually go ahead and machine it and use it directly for making your casting. So that's basically how we classify from a volume perspective. Going ahead, these are different technologies. We touched upon that. So today we have people printing polymers, we have people printing sand, metal, ceramics, wax, Kevlar, graphite. People are printing all sorts of exotic materials today for industrial applications, suiting different requirements. So basically, some of the broader classifications are listed below. Say, for example, based on durability, based on surface finish, based on detailing that is required for the part. Then application. Say, for example, you have so the technologies basically show that. So if you move from a lower durability to a higher durability, a smoother surface finish to a rougher surface finish. So these are all different names that are given on the right. You can see stereolithography, polymer jetting, binder jetting, fuse deposition, laser melting. Basically, some of them are for polymer material, some of them are for metal, some are for ceramics, some are for a combination today. So these are different technologies, and they've been evolving over the past 20, 30 years, and some of them are fairly new, very new. In fact, surface finish, rougher surface finish. So these are all different, and cost effectively you can print metal parts using the binder jetting technology. These are compact small machines which are being popularized. So going ahead, you can see the whole process process flow of additive manufacturing. What you see on the left side is it all starts with a 3D model. How does this work? So you have a 3D model. Anything that has a 3D model that can be converted into a 3D model can be 3D printed. So from a 3D model, we go ahead, convert it into a triangulation file. So basically, STL file is basically a triangulation file. Any part is broken down into triangles from a surface perspective, and then this file is sliced. So you slice it into multiple layers, and each layer information is passed on to the machine, and each layer is laid one on top of the other to get your final part. So that's basically how the whole process works. Now you can see that happening there. In the fourth step, you have the whole printing process going on. Once the process is done, then you have some finishing process which is done, which is, we call it as a post-processing. In this case, we have the end part based on some application, either through heat treatment or machining or other surface finish, surface treatment processes that we follow to finish the part and give it the final shape and form that we want. So we'll specify, interestingly, another aspect which is changing in the market is product life cycle. If you've seen, what used to take from a product development life, which used to be about 5, 6, 7 years, are all shrinking into 1 or 2 years now. So take an example of an automobile. What a car like a Swift took in its first generation to be modified, say it took about 7 or 8 years before it underwent a change or a modification. Now it's all happening in about 3 or 4 years. The second version of 3D printing came down to about 3 or 4 years, and the next version will go down even further, maybe in about 2 years. So people are getting restless. So every product is getting obsolete very quickly, be it mobile phones, your televisions, because the technology is evolving so fast. Now, one of the technologies which is really supporting it well is 3D printing, because what would otherwise take you many weeks or months to make your first casting part can be printed in few hours time. We've printed parts for automobile manufacturers where otherwise they would have had to cast it in about 3 months time or 2 months time, are all 3D printed in about 2 or 3 weeks time, and offered it to them for testing. Right now, as we speak, also a lot of the parts which are undergoing change are going through this process. In fact, a lot of BS4 to BS6 conversion happened through 3D printing route for those initial batches when they wanted to test it and see the functioning. So that way, AM is the most suitable process for this supporting this technology. Going ahead, so as I explained, different materials you can see on the top left. You have sand printers. These are polymer printers, multi-jet, multicolor printers. You have beautiful multicolored over 30-40 colors of printing available today by different manufacturers. Ceramics are being 3D printed. You can see that complex structure, which is almost impossible to manufacture. Graphite is being 3D printed. Metal we've seen, we'll see more. Diamond, Sandvik is a company who's been successful in printing diamond. Diamond has not only an ornamental advantage, but also is known for being the strongest material in the material that is actually found, and that is used mostly for cutting applications. So for that purpose, it has been 3D printed so that it can be used and made in large volumes and used for its application. So that way, different materials. We'll focus our presentation going ahead a little on metals. So you'll see a little more cases of metals going ahead. Next, so you can see this here. This is a technology called as laser powder bed fusion. If you actually see, most of the metals that are being 3D printed today are using this technology called as powder bed fusion technology. So what happens here is material in the form of metal in the form of powder is laid on a plate, as you can see here on the top image that is being pointed. So it's being laid like this, as you see, and then you have laser which comes and melts that powder and it fuses to the previous layer. So previously melted part is fused to the new layer of powder. So as in every layer is completed, the platform goes down on which this is printed, and the next layer of powder is laid. So you can see on the left side, the blue image actually shows you multiple of these layers of the powder which was fused into forming the part which is sitting in the middle of a big cake of powder. So now this layer of powder could be anywhere between 30 to 100 microns thick to get your part which is finally almost finished. So this is basically how it happens. So the power source could be either laser or electron beam. What you see on top is basically a laser beam which is deflected by a mirror. It's a 2-axis mirror which actually melts, which deflects the laser beam very, very selectively, accurately at a specific spot, and then melts the powder and fuses it to the previous layer. This is very similar to a micro welding process. So any material that can be welded can be 3D printed. So imagine you have heard of laser welding. So this is very similar to that, but happening at a micron level, very, very fine level. So that way you get your accurate part with the very less defects on it. Next. So what we have going ahead is a demonstration of this printing process. So there's a small video which shows you the 3D printing process. Here you can see there are two lasers printing two different parts on the left side, where the current layer of powder is being fused to the previously printed layer of powder. As the printing process completes, you have the next layer of powder which is laid. So in the middle, what you see is an image of a part which is already printed. So this part which is being printed after printing, and when we lift it up, you'll see the metal part is embedded in the middle of a big cake of powder. So when we extract all the powder out, when we remove all the powder out, what you see is you get on what you get on the right side. So basically, this is a printed part which is fused to the build plate or the base plate on which the part is fused, and this is basically cut and then taken further for finishing if required. Otherwise, in some applications, it's ready as it is and can be used. So that way, in a very short time, in few hours, you can actually get the part that you want. Going ahead, next. In this whole process, what you've seen at the metal 3D printing process, we discussed about powder bed fusion, PBF. So as I explained, about 75% of the printing that is happening in metal uses the powder bed fusion technology. The other one is DED, which is basically direct energy deposition or a direct metal deposition. In this case, basically what you have is a metal being fused through a coaxial laser and metal jet. A powder metal is actually sprayed using a nozzle onto a plate. Basically, this is similar to a 5-axis machining. If you've all seen 5-axis machining, you can imagine instead of the spindle which is cutting material, you have a nozzled body which is spraying metal and laser surrounding it. So basically laser melts the powder wherever it's being sprayed on. So that way you can print parts of any shape and size as required in this whole technology. And the third one is the new one, which is called binder jetting, which I explained some time back. It's also an interesting field where you have basically a binder, which is more like a glue, which is sprayed on selectively in areas where you'd want the bonding to happen. And then the next layer of powder is laid, and again, the binder, which is the glue, is sprayed. So this way you, at the end of the whole process, you get a big cake of part which is in its green stage, which is just glued together, and that will have to be subjected to a sintering process. Basically, it will be put into an oven which will melt the whole part and fuse them together. And then finally a debinding process where it removes the binder, and then you have your final part ready. So this is one of the newer technology which has come in the past 5-6 years time, but it's at a very nascent stage. So this actually shows you, this slide shows you about surface finish. So what you see on the left side is a very coarse thickness. Imagine we take it as a 80 micron layer thickness. So when you want a part which is which has to be printed fast, we end up choosing a coarse thickness. So this has an advantage of printing faster. You get your final part much sooner. But it's an economical approach. But the problem is the surface finish is very poor. You don't get a very finished part, so you'll have to probably subject it to some post-processing or finishing, machining here. On the right side, what you see, rightmost side, you see a thin layer thickness, say for example 30 micron layer thickness. Here the printing is slow, but it's almost ready to use in its final shape. It may be a little more expensive to use, but because you'll be taking longer time to print, because time is what decides the cost. But you also have an option of printing it in hybrid, what you see in the middle here, where you have coarser areas which doesn't need too much of finesse. You could probably go ahead and print it in larger thickness, and then maybe when you have finer aspects, you can print it in lower thickness. Eventually you'd want a surface finish as shown in the image at the back, so where you'd want a smoother surface finish, which is achievable through post-processing, which is finishing it through some post-processing process. So it's all about finding the right balance. So we explained about design for additive manufacturing. So we'll quickly run through this. So basically, this is a science where, as designers, we can sit and understand, apply a lot of AM techniques to find out how do we make parts more suitable for its application. So here, say, like we've told, you can create intricate shapes and produce them with lighter material or make it lighter. So if people who've used ANSYS, which is what you'd use to simulate weight optimization and ask based on certain conditions, ask ANSYS to throw out the most optimum structure. It normally throws out a structure which is in a maybe a bionic form, which is very weird in shape and size. So what we end up doing is to add a lot of material to make it suitable for manufacturing. If you've actually seen, though it gives out a very weird shape and structure, we end up adding a lot of redundant material, hence over designing to make it manufacturable. Whereas with 3D printing, we have an advantage where you can see the images in between. You have a lot of analysis being done. On the extreme end, you have a solid block of a bracket which is designed, which goes through multiple rounds of iterations of analysis and simulation, which finally tells, look, you need material only in these areas for the kind of strength and load that you've actually asked. So that ends up deciding how the shape and size should be, and that can be directly taken onto a 3D printer and printed and used for its final application. That way you have saved not only material but also a whole lot of time in manufacturing it the conventional way. So this way a lot of advantages are there, and design for additive manufacturing is a very important subject. Fantastic softwares are being made available. Almost all software manufacturers today are gearing up for this science, where they're taking you from a seamless integration, design, simulation, analysis, manufacturing. All these are being done on a single platform, which earlier used to be done on different tools. Going ahead, you'll see some more examples of DFAM. You can see this part here. This was basically a bracket for Airbus. An existing part used to be big and bulky like this. Still an aerospace part, which is quite light conventionally compared. When you did a topology optimization, you ended up getting a part which is seen on the right side. So this is actually a part which has been put to test and been used. So where you apply topology optimization. One of the biggest areas of AM where applications being used is aerospace. You can see some of the advantages are very little wastage. You have a lot of cost saving when you have exotic material like titanium and others which cost a lot of money. If you've seen aerospace parts, when you print, about 95% of the material is scooped out, and finally you get a very lightweight structure. So you put a solid block and get a very thin structure which comes out. Here you can print that directly. That's the advantage. Part consolidation, we'll look at that going ahead. So you basically can print multiple parts together. So here's another interesting example where you have electric vehicle motor housing, which is 3D printed. So as Sir rightly pointed out, electric vehicles also are hard pressed for weight. Today, if you can make a motorcycle or a scooter which is 3D printed, which is an electric vehicle, if it has a mileage of say 70 kilometers per full charge of battery, and if you can make it a little lighter, maybe you can push it to 80 kilometers. So that way, it's a huge USP for these automobile manufacturers. So lighter automobiles are the order of the day. So that's where you have a lot of people working towards that. People like Aether and many others have already started exploring printing parts of polymers and making them lighter. Going ahead, so you'll see another interesting aspect of 3D printing is not everything that we tell as an advantage of 3D printing is applicable. So there are aspects which we need to follow in terms of making it suitable for printing. So not all parts are ready for 3D printing. So there is something called as supports that get printed along with the part that is actually required. What you see here is that basically the any part which has an overhang needs to be supported from the base plate. This is basically similar to a structure that you're building where you have overhanging scaffolds which need to be supported. Otherwise, you'll end up dropping it down or deforming or warping the part. So you see these images here, which shows you that where supports are provided. The red one and the blue one are basically supports required to support that overhanging structure. Now, this can be overcome by doing a small design change, which is also a part of the design for additive manufacturing, which you see that by doing a small modification, like which is called a self-supporting structure or self-supporting profile, which actually where we went about modifying a flat surface on the previous image by giving the small angled material that ends up making it self-supporting. Now, this allows parts to be printed without support. So all this is also a part of the design for additive manufacturing. And also you have cooling channels when you have when you're making molds, which we'll see in a bit. Design for them also will be better when you go for a larger size. You'd have to use a different channel like this which is self-supporting profile when you want to do holes which are larger than a specific size that is dictated by the process. Next. So this is what we mentioned in terms of lattice structure. So you can see these here. Left side you have a manifold block which is actually made of lattice structure. You can see when we say lattice, it's all mesh kind of structure. The external structure remains same, but internally you do a lot of mesh kind of design which has very less material. The strength remains the same. Functionally it's as strong as the solid material, but it's much lighter and hence much better. So on the right side, what you see is an impeller blade, which probably goes into either an aircraft or a turbocharged automobile component, which when made lighter like this can run much faster. So some of those turbocharged parts run up to about 30,000, 50,000 RPM, and when it's made lighter, you get so much more better application. You can run it for much higher RPMs going ahead. So that way, for making lightweight parts, 3D printing is the right approach. So what you see next is, let's wait for it to come up. So yeah, so market segments. So today there are different markets who have adapted 3D printing: medical, aerospace, automobile, tooling, dye industry, and engineering. So we'll look at some of them. In the medical industry, one of the most popular ones, we'll skip this going next. So in the medical industry, one of the most popular, okay, so we look at the aspect is medical implants, where you have implants. What you see on the left are like your cranioplast implants, which is basically a portion of your skull, maxillofacial implants, your face implants, mandibular implants, which is basically the jawbone. All these are being 3D printed today. Today, when a person meets with an accident on the and the doctor declares bone loss, there are two choices. They can choose a standard generic implant, more like a fixed size of shirt, say 40, 42, 44 size shirt, or it could be a custom suiting the design of the particular patient is actually made and supplied to the patient in a very short time. So basically a CT scan or an MRI scan file is required as an input, and that is used to print this part and supply it to the patient. Similarly, you have hip sockets, dental copings, knee joints, hip joints, acetabular cups. All these are being printed today, very specific to a patient's shape and size. Next. So basically, they say going ahead, a lot of medical implants are going to be done not only globally but even in India. There's a big adoption of 3D printing, and the niche areas could be some of these, like cranials and hip implants and other orthopedic implants. Next. So we look at aerospace. Now, aerospace, one of the biggest advantages is weight reduction. So you see this bracket on the right side, which originally weighed about 2 kilo or an excess of 2 kilo, has been brought down to about 766 grams by 3D printing optimization or topology optimization, where the strength remains the same, but the part has been completely optimized. So this way, when parts are done, they pose a huge advantage to aerospace industry. You can see this bracket at the bottom, which is full of lattice. You can see the structure. It's basically, this is the structure called as bionic structure, which originally was a big bulky structure, has been modified to make it very very specific to the application that is suiting aerospace, and also making it lightweight by putting lattice structures, the mesh design that you see, which makes it very suitable. From a strength perspective, it's same if not higher, but much lighter. This way, lighter aircrafts mean further the distance that they can fly. So that way, today, if you see some of the newer aircrafts that are coming in, are able to fly much longer distances. We have part count reduction. So here you can see on the left side the fuel nozzle. Fuel nozzle basically is what goes into a GE engine, and this has been shown. You can see that 20 individual pieces or parts have been integrated into a single piece. So one part is actually a combination of 20 individual pieces. So this has 5 times more durability and 25% lighter. So not only is it better from durability point of view, but also lighter. As we speak now, this is not just in prototyping, but this is already gotten into production stage. So you have more than 50,000 of these nozzles already flying on GE engines. So every GE engine has about 4 of these nozzles. So an aircraft which has 2 or 4 engines would have multiple of those fuel nozzles. On the right side, what you see is basically a catalyst engine from GE, which is fairly new, launched about a year and a half ago. Here, 855 individual pieces were integrated into 12 assemblies or 12 pieces and 3D printed. The advantage is it's 20% lower in fuel burn. It consumes lesser fuel, and it's also 5% lesser in weight. Now, the advantage also is you have fewer bill of materials, you have fewer parts. Now, as designers, we all know, as and when you have more parts, more the reliability issue. You have every joint poses your stack up tolerance issue, and this overcomes that by integrating multiple of these parts. That's the advantage which is coming up in especially in aerospace. Going ahead, cost effectiveness. So if you actually see, as I explained, manufacturing is cheaper because as opposed to printing something which is a solid block of titanium, which could cost lakhs of rupees, and when you remove out your part is nearly 1/10 or maybe 1/20th the weight, you're better off printing it directly, where you have very less scrap coming out, and your part is very cost effective. That way, for materials such as exotic materials such as titanium, Inconel, 3D printing seems to be the more suitable route. And lastly, we have on-demand manufacturing. This is an interesting area which is coming up not only for aerospace but also for automotive. So what is interesting here is we have a lot of manufacturers such as Daimler and others who have a commitment to their customers, telling they will stock spare parts on account of the customers as long as the vehicle is being put to use. So, for example, a person can be running a Daimler truck or a Mercedes-Benz car which is 20 years old, but Mercedes has committed, telling we will keep the spare parts on your behalf. Now, because of this, they have billions and billions of euros worth of spare parts, which is getting wasted. And that's a lot of money. So instead, what decision they've taken is going ahead in the near future, which they've already started, is they will only keep 3D design, 3D model of the parts. And when there's a requirement, say, for example, in Mysore, the local service center will be sent the 3D model and they can get it 3D printed. Even if it's going to cost 10 times the cost, it's okay, because you've saved up the cost of keeping inventory of those parts and waiting for nearly a month to get it from some corner of Germany into Mysore, which would take a lot of time and effort. And that can be saved by 3D printing locally. So this way, on-demand manufacturing, only when there is a demand for a part or a spare part, it will be manufactured in very short time. That's picking up not only in aerospace, but also in automotive. So going ahead, so this is an interesting case as we speak. This engine of Boeing 777X has already been flying with 300 3D printed parts. The engine's name is GE9X. This is already available. All this is open source information. So more than 300 3D printed metal parts are being used in this engine, and it's being flown. So gone are the days when 3D printing can be considered as just a prototyping or a sampling process just for visualization or validation, but it's actually gone into full production. You all know any aerospace part needs a very, very solid airworthiness certification, which means it has to be proved that it's really worthy of flying for many years. So this has been going on for past many years. In fact, for the past 5 to 8 years, the validations have been going on. That's why the adaptation is been low in the past, but now you'll see rampant adaptation of these technologies in industrial areas. So this is going to be the future for aerospace and other aircraft. So you'll see it in the next slide, what the plan is for aerospace industry. So by 2030, we'll be looking at AM designed airframes. So which means not only are we looking at small parts of the aircrafts, but the aircrafts will be designed to suit 3D printing process. They will keep only 3D printing or additive manufacturing in mind to make aircrafts. So this way, maybe aircrafts will have enough fuel. They'll be able to carry enough fuel to fly from maybe Bangalore to Las Vegas or Los Angeles non-stop, which probably today is not possible. So a 20-25 hours flight should be very straightforward in the next few years' time. So that's the beauty of aerospace. Now, in the automotive segment, we've known rapid prototyping. That's been there for a long time. It's been quite popular. People have been using it to validate, visualize their designs very quickly. But another advantage is generative design. We'll have a look at that in the next slide. Basically, it's all about designing and printing to validate your design to make sure it actually works instead of doing it on a simulated platform. We discussed spare parts manufacturing. So we'll look at the next slides, which gives you examples of 3D printed parts. So you can see this left side, Bugatti is being printing some of their parts for their special cars using this SLM technology. Or selective laser bed technology. So what is interesting is, as I explained to you in the product lifecycle slide, 5 to 6 years is what it used to take to develop a car, which means if you're, as we speak, they're developing an automobile which is to come out in the year 2025 or 26. Now that is changing because people are demanding, technology is modifying or getting changed so quickly, they cannot afford to wait for 5 to 6 years. So people are expecting things to come out in 2 or 3 years time. So 3D printing is the right route, which is being adapted by many manufacturers in doing this. So you can see this on the right side here. There's a small engine block which would conventionally take about 4 to 6 weeks. This was printed by us in 48 hours. So just an example to tell you how time is everything and how it's being shrunken by a process like AM. Next, what you see is the generative design concept. So you can see this is basically a seat belt assembly by General Motors for one of their next gen cars, which when they sat to design, they found multiple design concepts, which they finally chose one of them after 3D printing and actually putting it to test. They put the whole assembly, they printed the whole set, multiple of them, because as I said, if you remember, variety is free in 3D printing, which means you could print 15 different varieties of a part weighing around almost the same, or you could print one variety of parts 15 different times, or 15 numbers. They'll all be in the same. They'll all be the same cost. So that way, people are putting actual design into use and then validating it for themselves. So that's generative design. You'll see this interestingly in the next slide. 20 individual pieces were put together. Sorry, 8 individual pieces were put together in this assembly to make it as a single piece, which this way it was not only lighter but also stronger. So that's the beauty of DFAM and also 3D printing. So that was automotive. This is just a summary of the whole thing. So we have Renault, which is doing, we'll see a small video where 200 different parts of an engine from a Euro 6 engine was printed, where 841 parts were brought down to fewer numbers, and they use 3D printing here, not only to reduce the number of parts, but also weight reduction. We'll just have a look at a short video which shows this whole process. You can see here, the original design was taken, and then a lot of DFAM techniques were done, modified, lightweight. So you can see 42% lighter. Each portion of the, so you can take a rocker assembly bearing cap, take it, make it lighter, and multiple of them got printed and put into this. So you have a rocker arm, 36% lighter, multiple of them, again put it back in. So you take an engine, cylinder head, cylinder block, 80 parts were integrated, which means your runners, nut runners, a whole lot of other things which would have gotten integrated. All of them were put together here again. Parts got integrated, 45 parts got integrated into the cylinder head, which otherwise would have been individual pieces. So your 841 piece assembly got down to 200 parts lesser. So that way your BOM, or your bill of material for this, got reduced, and finally your whole assembly became faster. So that's basically the whole show. Similarly, Honda has done a lot of lightweighting on their crankshafts, which are made lighter and better. So different automobile manufacturers are working on it. Even in India, Bajaj and many other automobile manufacturers gotten into it. Now, this is another interesting case where you can see the lattice structures. As I explained, people have been trying out different parts. It may be costly today, but they all know it's only a matter of time before which this technology is going to come in and then take over the conventional way. So then people don't want to be starting to learn. So people want to invest time, effort, and money in learning the process, adapting, and finding out suitability for their application. Finally, when the technology really booms, they'll all be ready with solutions, and they'll adapt it very easily. So in this case, you can see F1 Alfa Romeo cars have about 143 metal parts which are being 3D printed and integrated into their racing cars. So like this, almost every industry which has niche applications are using that. We discussed the on-demand spare parts. We can skip this. So any remote location spares can be made available to 3D printing. Another interesting application is tooling. Tooling, when we say, is basically plastic injection molding or any other molding process. So conventionally, if you see, a molding process has about, so you can see on the right side, the whole molding process has about 65% time as cooling time, because any plastic part that you actually injection mold needs so much cooling, because if you try ejecting it out faster, you'll end up warping the plastic. That way you'll be spoiling the whole part. So that way they end up cooling it naturally. Now, next slide, what you see is this mold, which is there on the left side. This is how the cooling is done, where they have a straight hole which is drilled, called as a rectilinear hole, through which cooling water is passed to make it cool. Whereas on the right side, what you see is a conformal cooling channel, which is conformal cooling channel is where you have a channel which takes the shape and size of the part itself, and that way gives much better cooling and much uniform cooling and makes it much faster. So through 3D printing, we can achieve this. So all the aspect that you see on the right side, which cannot be done conventionally, where you cannot drill holes of this shape, can be done only through 3D printing. So we have been doing a lot of molds also, where 3D printed molds have shown a lot of improvement, either in the form of warpages or removing of these air traps, or even getting better surface finish of injection molded parts. So this is basically one of the key advantages. You can see this warpage on the right side, where the part gets twisted, or when it's removed, it doesn't give the actual form or shape that is required. So that is mainly because of non-uniform temperature distribution. Next slide, you'll see uniform temperature distribution because of 3D printing. What you see on the left side is the red zone is because of non-uniform temperature distribution, where because using conventional cooling process, you can only achieve limited cooling. Whereas on the right side, what you see is conformal cooled channel, where the cooling water goes all through the heat zones, which when you have molten plastic injection happening, and because of uniform temperature distribution, you can see the thermal graph there, which shows uniform temperature. That way you can eject the part much faster. We have seen 30-40% improvement in cycle time using conformal cooling channel. Next. So these are some more examples. You can see what used to take 50 seconds on the left side using conventional way got reduced to about 33 seconds, thereby saving about 2 lakh rupees. Next, you'll see something similar where customers saved about 40% in time, again because of conformal cooling. And here about 12 lakh rupees was saved because again of uniform temperature distribution. So that way it's a big advantage. So going ahead, even in the foundry application, what we've seen is patterns. As I explained initially, 3D printed patterns is one of the biggest advantage, where you can print these patterns and directly take it to your casting, which will make it much more faster and much more advantageous in terms of complexity. So the Digital Foundry is what they call it. So this is again another interesting subject. Next. So from an engineering perspective, today people are printing different sorts of parts for your pumps, valves, and your hydraulic manifold blocks. Jewelry is being printed, gears assemblies are being printed. That way, even in the engineering space, a lot of work is going on using the 3D printed route. Next. So what does the future have in store for us? So as I explained, mass customization, what used to be a customer would be able to interact through a lot of retail source. This is being converted, wherein customization is happening in terms of making sure every person gets what is very specifically required for them. If you see in the shoe space, I don't know if you've all heard, already people like Nike and Adidas have the sole of the shoe being 3D printed specific to a person's foot size and shape. So instead of choosing a 9, 10, or 11 size without knowing what type of foot I have, today you will be made to walk or run on a treadmill, which is being watched by a camera, which can see your foot profile. It's called as a gait analysis. And that is being mapped into defining what sort of pressures are being applied on your foot from the bottom. And a foot insole is being made very specific to your size and shape. So this is being made in large volume. So like this, a lot of people have been working on customization. So remember this word, it's called mass customization, where high volumes of parts will be made, but they'll be each specific to a particular customer. So automobiles also may change to a specific taste of a customer going ahead. So there'll be a lot of distributed manufacturing also going ahead. You can see here future supply chains are going to be something like this. Current traditional manufacturing follows a whole lot of indirect route, where you have manufacturers routing it through wholesalers and retailers before it reaches a customer. Whereas in additive manufacturing, someone could approach the manufacturer directly and it could be made available. So basically, it's moving from a B2B space to a B2C space, where a direct consumer can talk. Like I said, you have service bureaus like ours, where people can walk in and tell, look, I need a part which is of this particular size or shape to be made, and it can be made available in a few hours time. So that way, a lot of the project works and many others are being made through 3D printing. So with the future, as this topic is rightly aimed at, is going to be a big blend of Industry 4.0, where you have a lot of augmented reality, you have virtual reality, you have Industry 4.0, you will have people sitting in America sending a program which has to be printed in maybe in the smallest village of India or even Africa. through, and they'll be controlling it through a digital platform where everything will be uploaded on the cloud. All data will be available, and then someone will manufacture it automatically, and then that comes out and gets dispatched to maybe someone in Europe. So the whole science is going to get changed. It's going to be a global village where people are going to have access from different parts to parts of the world, sitting anywhere and trying to reach out and manufacture something and distribute it and make it happen. So it's all going to change going ahead. It will not be the conventional way of doing how we have been doing. So that's the beauty. And one of the technologies which fits in well is additive manufacturing. So that's us. So we basically, as I said, AMACE solutions, we offer design, engineering, analysis solutions. We print different parts in metal. We offer post-processing. We finish the parts and give it to suit the application or requirement. We do a lot of R&D in terms of developing parameters and materials, and how we do it. So going ahead, we'll see a few quick examples of what we've done. So materials, we can skip this. So next you'll see some of those interesting case studies of what we've done. So this was basically for a Formula SAE car student project where an electric car was being developed, and we printed these hubs for them. And you can see a lot of lattice structures, lightweighting was done. We did DFAM for them, and then we did this for the rear wheel hub. This was printed in aluminum and given to them. Next. This was again for an electric motor. So this is basically a motor manufacturer who was making motors for EVs, and in this case, a lot of lightweighting was done. You can see where those ribs are there. Conventionally used to have a lot of solid material, but it was made suitable for 3D printing. And conventionally, we used to follow a die casting route, but with 3D printing, they were able to achieve it in a very short time. We also machined this part and gave it to them. Next, you see this is basically a convention. This is a conformal cooling application where you can see there's a cut section of a mold or a die which was 3D printed. You can see the section inside has holes and channels which are in a very circular or windy way. You'll see another slide next which shows this very interestingly. You can see this here. This is basically a mold of a plastic injection molded part where you can have these curvy linear holes where they go in a circular way and then cool the whole block uniformly without having to actually go through a very cumbersome process. This is done through 3D printing, and a cut section is shown to you in the model there. This was a die casting application that we did for a TVS group company where you can see on the left side, you have these channels which go all the way up and then bring down. In this case, the customer's goal was better surface finish because of uniform temperature distribution, where you have a cooling liquid which goes all the way up and brings it down. Similarly, another application for a forging process where you have material, basically a graphite lubricant which got sprayed through the small vents which came out of this forge punch, which we were able to do. This is still under testing and development. Once this gets done, we'll probably be able to do more on the forging space. Next. So these are some of the nozzles. I explained to you variety is free. In 3D printing, the advantage, as I explained, you can see here more than 8 different varieties of nozzles were printed, all at the same cost, where this customer was using it for a spraying application, and they found that this was quite helpful. And now they've gone from prototyping to batch production to now mass production. So they've been ordering on this nozzles which will be made in high volumes, but each of a different design and suiting a different purpose and application, made very cost effectively through 3D printing. So we've been doing aerospace parts also. You can see this here, an entire engine assembly were put together by printing them in pieces with very minimum machining requirement, and then finishing and then finally taking it up. So this way, this is basically a prototype that was done for us. Like this, we've been working with different aerospace aviation industries, including ISRO. So the next slide will show you we were a part of the Chandrayaan-2 project, wherein there were 3 parts. If you all remember, there's a lander, there's an orbiter, and there's a rover. The rover is basically an AGV which comes out of the lander, and which was supposed to have gone all around the moon, making collecting information from the moon surface. Now you see this India logo on the left side. We printed this in aluminum and gave it to them, which was pasted on the wheel of this rover. You can see the simulation. It was supposed to have laid the printout of India on the moon surface. You can see that small India logo on the moon surface. So the idea was to bring out India's signature on the moon surface when this happens. Unfortunately, the lander did land a little too hard, because of which the rover could not come out. But nevertheless, there are many 3D printed parts made in India by ISRO sitting on the moon surface. So we are not very far behind the other developed countries in adapting the newer technologies. So that's what we've done. So you can see we did this in 8 hours. Imagine printing India's signature to be taken on the moon in less than 8 hours time. So that's what technology has brought us to. So that brings us to the end of our presentation. If there's any questions, please do ask. You can email us. Our email ID is there. Our numbers are there. Our website is there. Most welcome to look us up. I again thank you all for this opportunity to address the gathering on this interesting and exciting subject of additive manufacturing. Thank you.
Balaji sir. Hello, Balaji sir.
So,
Sir, if you have any questions, you can ask, sir.
yeah. Any questions at all?
Vinod,
Yes, sir.
audible? I am audible.
Yeah, sir.
Sir, audience, participants, if you have any questions, you can ask the questions. You can unmute yourself and you can ask any questions if you have any questions related to the topic.
Hello, sir.
Yeah.
Sir.
Myself Ravi Kumar from Venkateshwar Polytechnic, Bannerghatta, Bangalore, sir.
Yes, sir.
Sir, my question is, in the subtractive machining process, manufacturing process, we will get lots of wastage, no?
Yeah.
Those wastage can be utilized and make a new component by using adaptive manufacturing process. Is it possible, sir?
Now, my answer will be yes and no. Now, it depends on what is your application. So we can see there are different ways of additive manufacturing. So if you're looking at putting material together to form a part just for visualization without any industrial or functional use, then maybe you can do that. But the problem is when you have a used material, it has a lot of unwanted, undesired particles which get mixed with it. And when you're talking about this process of additive manufacturing, you're touching a huge amount of metallurgy in it. Now, the last thing that you'd want is any adulterant entering into your part, which is supposed to be homogeneous. So unless it goes through a thorough process of cleaning and processing, it may not be useful. But people are. So basically, we are only processing powder. Now, how the powder get manufactured could be through processes such as, it basically, the main process is gas atomization. Now, for a gas atomization to work, you could have, it's basically starts off with an ingot of material, say, for example, an aluminum ingot or a stainless steel ingot, which is fed in as an input material to make this powder. Now, an ingot could use some of this used scrap which comes out of subtractive manufacturing, which goes through a lot of processing and then made re-melted and brought out as an ingot. So directly, we may not be able to make powders out of the scrap of subtractive manufacturing, but a lot of the waste can, I'm sure it is happening today because there's only limited amount of material available globally. So especially materials such as titanium, which is extremely expensive, you're better off melting them, recycling them, and then bringing them out as powder. But it's a subject which goes through multiple cycles. There's no ready machine which can take in scrap and then bring it out as a powder and be used for 3D printing.
Okay, sir. Understood, sir. Thank you, sir. Thank you very much.
Yeah, thank you. Thank you.
Hello, sir. Hello.
Yeah.
Good morning, sir.
Good morning.
My name is Subramanian from Ace Polytechnic. My question is that what is the accuracy, dimensional accuracy we can achieve compared to our conventional process, like CNC machines? We get very unique dimensions. Is it
Yeah, that's
possible
right.
to get in 3D printing in overall product dimensional accuracy? How can we cope up to that is 3D printing?
Yeah, so basically, right now, what is being done in large volumes, which is the kind of area that we are in, where a lot of printing is happening, the powder bed fusion technology, the accuracies that are there are around point 0.1 plus or minus 0.1 mm to plus or minus 0.2 mm. So that's where we are at this point in time. But it depends on the laser beam spot size. The spot size that we are working on is around 70 to 80 microns, which is why we're getting about 100 microns of accuracies, 100 to 150 microns. But for some of the finer applications, people have even gone down to about 10 microns laser beam spot size. When they use that size of laser beam spot, that have to go for finer powder particle sizes also. For very fine, very specific applications, there have been successes where people have gone to very tight tolerances of manufacturing. But what we normally tell is 3D printing cannot replace machining or manufacturing, machining the conventional processes completely. It will still have to be subjected to aspects such as a finish machining, because just that skin cut of finish to get that final tolerance or accuracy may still have to be done based on, using the conventional way. So otherwise, 3D printing can take care of your casting, your roughing, your semi-finishing, but the final finishing may still have to be done the conventional way.
Okay, sir. What about the flexibility in materials, sir?
Yeah, so right now there are about 8 or 10 very prominent materials which are there available in the open market. But a lot of research is happening, and like I said, any material that you can actually weld, if it's a weldable material, it can be 3D printed. So it's only a matter of time. Once applications start coming up more and more, the manufacturers will start investing, and when the volumes increase, the cost will come down, and the recipe also will get generated. So a lot of this is happening. See, it's not a very straightforward thing to 3D print, because you need to make sure you get the right set of parameters to touch the metallurgical aspects of it, and make sure you get the right shape, and without any deformations or defects or blowholes or any other aspect that comes on a casting process, which is what we have to safeguard. So it is happening as we speak. A lot of new materials are being introduced, but what is prominently available are about 8 or 10 different materials.
Okay. So, okay, sir. And also, sir, another thing. Hello?
Yeah. Yes, sir.
Sir, the materials before pre-processing of the 3D printing,
Yeah.
so that the material should be in the powder form.
Yeah,
powder
that's right.
form or powder form. So
Powder
again,
form.
that
Yeah.
will
Further,
be,
there's a powder bed technology. If you have a wire fed technology, then power material is available in the wire form also.
okay. When you convert to powder form, again, that is also a cost. It relates to the cost of that material overall manufacturing process. Again, that is also a drawback. So immediately we cannot fit to the raw material cost factor if you take powder material. Okay, that is so. How can we overcome that process?
So basically, it is an expensive process today, but where people see value in it, they are going to it. And with time, we have the cost of manufacturing, also cost of powders coming down, cost of machines coming down. The whole process is getting more productive. This way, if you see what used to cost X about 10 years ago, today it's already costing about 0.1x. So we've known of certain parts which used to cost about 25,000-30,000 to make. They're all sitting at about 2,000-3,000 rupees today, even in metal. So I'm just giving you a fictional number, but the costs are coming down. So it's only a matter of time before which a lot of it will get even more cost effective.
Okay, thank you, sir. Thank you.
Sir, one more question.
Yes, sir.
Sir, is there any opportunity to do innovation in bringing out a scrap material into a powder suitable for additive manufacturing process?
Sure. Opportunities are endless. I mean, I'm sure a lot of people who did think early and try out they are the ones who've been innovating interesting things globally. So I would definitely say it's all about trying and experimenting. You can get in touch with some of the powder manufacturers in India and see if you can collaborate, because see, the whole process of manufacturing powders is a very expensive process, which means the whole equipment that is required to invest in making the powders would run anywhere between 30, 40, 50 crores, and the yield is less than 25%, which means you put 1 ton of stainless steel, you end up getting only 25% of powder, which is suitable for metal printing. Unless you have a customer base for the other portion of the material, then you're wasting a lot of time. So that way it ends up becoming more expensive. So it's a catch-22, but I wouldn't discourage you. You're welcome to get in touch with different powder manufacturers who can probably share their views, and then you can see how you can contribute in terms of either research or maybe taking up a practical case.
Okay, sir. Thank you, sir.
All right, great. Thank you all. Thank you again. Thank you for this opportunity. You're welcome to visit us, Dr. Kapilan. You're welcome to bring a team from the institute to our college. I mean, to our facility. We'll be happy to show you in physical form. Of course, things are a little challenging right now in terms of visits, but once the COVID situation settles down and we are a little more movable, agile, then I think I welcome you all to visit us and have a look at what we are doing and how we are doing, and give you a better idea of the whole technology.
Thank you, sir. Sir, it was really an excellent presentation. We thank you for sharing your knowledge on latest technology. Your presence has immensely enhanced its importance, sir. We are extremely grateful to you. Thank you very much.
Thank you so much. I'm very glad. I'm very glad. Have a wonderful rest of the program, and I wish all of you the very best and success. Thank you again.
Thank you very much, sir.
Thank you.
Dear participants, we will share the Google form in where the feedback and the quiz has to be given. We request you to submit the Google form once you get that. After we share the Google form. Thank you. Thank you, one and all.
ಕ್ವಶನ್ ಕೇಳಕ್ ಕೈ ಎತ್ತಿದ್ರೆ